So the agenda for today, comparing two variances, assuming that our data comes from a normal distribution, is we're going to set up the hypothesis test. We're going to look at the distribution of the test statistic under the null, the alternative. We're going to investigate how to calculate power for this comparing two sample variances or two population variances, and then we're going to illustrate this in R. So the quick setup is we have data, two different sets of data. Both are normally distributed with some mean and some variances. They don't have to be equal. Sample sizes also don't have to be equal. And these are the population or the sample variances, the unbiased estimates. We're going to conduct this test at the alpha level, and the test statistic is simply the ratio of the sample variances, the unbiased sample variances. So then the test that we're going to do is we're going to see, are the population variances equal or are they not? Now this is equivalent to, and I'm showing you this because this is what they assume an R. Now if you notice, if you divide both sides or divide that over, then you get a 1 here. But really it could be any ratio, and this is what they do in R. There's a parameter that you can put in any ratio you want. The default is 1, which is equivalent to, are these equal or are they not? And we'll just assume the R equal 1 case. So under the null hypothesis, the variances are equal. This is an F distribution. So you have to take our test statistic, multiply it by the population variances, and it's a central F distribution with N1 minus 1 degrees of numerator degrees of freedom and N2 minus 1 denominator degrees of freedom. Now when H1 is true and the population variances are not equal, well, this is actually still a central F distribution with N1 minus 1 and numerator degrees of freedom, N2 minus 1 denominator degrees of freedom. So it's the same distribution distributed the same way. So how in the world can we calculate power? Well, this is how we do it. So when we calculate power, first let's assume that we're under the null, because we have to calculate the critical value, or the cutoff value. So this is an F distribution with numerator and denominator degrees of freedom. We're assuming that the variances are equal. So now to find these regions, we want to find the probability that we reject the null hypothesis, given that the null hypothesis is true. That's the definition of alpha. Well, that is this is equivalent to the probability that our test statistic F, the ratio of the sample variances, falls in the rejection region. Okay. Well, to calculate these probabilities, you have to transform it to some distribution that is known. Well, you don't have to, but that makes it easy. So if we take this distribution or our test statistic and multiply it by the population variances, then this becomes an F distribution. And so the probability that F is greater than some constant C2 is equivalent to this. We're multiplying the same quantity on both sides. Well, under the null hypothesis, this ratio is just 1. So we find C2 in a central F distribution. Okay, so this ratio is just 1, and so C1 is left. Now under the alternative hypothesis, to find power, what's probably that we reject the null hypothesis, given that the alternative is true, is actually the same thing. It's the probability that we're in the rejection region. And we take our test statistic times the ratio of our population variances. So remember that if we're in the alternative, we're assuming that the population variances aren't equal, and we have to pick values for that. And so we pick values, and well, this ratio is not 1. So the interesting thing, and you'll see when we illustrate in R, that the cutoff value shifts. It's the most bizarre thing, and you'll see. But we do a quick simulation to validate this, and I'll see you in R. Okay, I'm in R on a Ubuntu Linux machine, and we're going to compare two variances. We're actually going to calculate power and sample sizes for comparing two variances test, and we're going to assume it's normal data. Null is the variances are equal, the alternative is that they're not. And to illustrate this idea, we're going to pick sample sizes. So population 1 will have 22, population 2 will have 33 observations, and then we'll create some data to plot. And this is an F distribution with 21 numerator degrees of freedom and 32 denominator degrees of freedom. So when you conduct an F test, you calculate the test statistic, which is the ratio of the variances, and then you see if it falls in the rejection region. So let's calculate the rejection region. And here it is. The test statistics in here, you reject the null that the variances are equal. And if it's not in the rejection region, you conclude that there's not enough evidence to reject that the variances are equal. So here, to calculate power, we have to assume that the alternative is true. And so let's just pick values. We're going to say variance 1 is 4 and variance 2 is 2. So now, to shade in the, it's really not called the rejection region, but to shade in the region that we have to be in to calculate power is the following. So here, if we're in this green area using this same curve, then that's considered power. And to calculate power in this case, so true variance is 4 and 2, sample sizes of 22 and 33. The power is 41.9% or 42%, which is not a lot. We probably want to be around 80%. And I'm using the PF function, which is the cumulative distribution function for F, and I'm calculating the value here using a QF, which is a quantile function for the F. Okay? And this is it. But let's calculate the needed sample size. Now we're going to assume that we start out with 22 observations in each sample, and then we're just going to increment by 1 to each population, calculate power, and we're just going to repeat and repeat until it's 80% or more. So let's do that, and it's finished. And we need 68 subjects per arm to have 80% power to calculate, for an alternative of 4 and 2. And to illustrate this within R, we're going to look at a little simulation of 10,000. We're going to have our sample from a normal distribution, N1 observations, a standard deviation of the square root of 4, and population 2 will have the square root of 2, which is V2, and we will just run this little simulation to show you that indeed we do get 80% power, 80.9. Now, to me, it's interesting that it's not the rejection region, but the area under the curve changes when we're comparing two sample variances. And I may end up putting this on one of my statistical theory videos on why this exactly works. But it's pretty fascinating how this all works. Anyway, hope you enjoyed it.